In 14.3, we talked about partial derivatives. We're now ready to talk about what it actually means for a function of more than one variable to be differentiable and for its derivative to exist. And so that's what 14.4 is about. It's called tangent planes and linear approximations, and hopefully that will become clear as we talk through this. Okay. I want to just remind you that if I have y equals f of x, just a real valued function of one variable, what it means for that function to be differentiable at a point. So if I have an x value, x naught in the domain, the function's going to be differentiable at that point if the derivative exists. But of course the derivative is just the slope of the tangent line. So a function is differentiable if there is a line that we call the tangent line that does a good job of approximating the function. We would call that a linear approximation of the function. It's a linear function, in this case because it's a real valued function of one variable. It's a curve, but it's a curve that doesn't curve. The graph is just a straight line. Okay. And of course, for a function of one variable, the line will exist if the slope exists. So we really focus on, can we calculate the slope of that line? Well, if I have z is a function of x and y, and I'm just going to recycle the name f here. Obviously, this function f is a different function from that function f. But if I have that, that's describing some sort of a surface in 3 space. Now my surface might be something like the top half of the sphere. So I've got a model of that here. Now this model is imperfect because this is a solid version of things. And of course the graph of a function is just going to be a surface. So I used this model for several years, and then a wonderful student said, do you get tired of telling people to pretend it's hollow? And she got me this lovely Mickey Mouse hat. It even has my name on the back. I mean, it's beautiful. Okay, and this would be a hemisphere that is hollow. So this would actually be a surface. Of course, this one came with ears. Now, the ears aren't actually part of the graph of the function that would give me the top half of a sphere, because the ears make it fail the vertical line test, but they're so cute, I couldn't bear to take them off. So we're just going to compromise. I'm going to wear the model of the sphere and that fits on my head, at least until it falls off or drives me crazy, and I'll use this as the model. But we do have to then go back to pretending that it's hollow. So we're just talking about the surface of this hemisphere. Now, if I wanted to come up with a linear function of 2 variables that estimated this, well, a function of 2 variables is going to give me a surface. A linear function is a surface that doesn't curve. It would be a plane. So we'd be talking about finding a tangent plane to our function. That would be a plane, a linear function of 2 variables that does essentially what our tangent line does for the curve. It does a good job of approximating the function at and near the point of tangency. So I'm going to try to focus on, can I create a tangent plane? Can I create a linear function that does a good job of approximating the function that I have? Okay. Now I'm just writing out a generic function here, but I'm sort of thinking of the hemisphere as my model, and ultimately when we do a specific example, we will work with a top half of a hemisphere. All right, now if I think about what I have with my function of one variable, okay, our tangent line, in order to get a tangent line, I would of course need 2 things. I would need a point, so we would have x naught, f of x naught, and then I would need the slope. And of course the slope is just f prime evaluated at x naught, evaluated at that point of tangency. And then I can create the tangent line just using point slope form. I always remember that by just thinking rise is equal to slope times run, where I would calculate the run and the rise using this specific point and then an arbitrary point x, y. So that the rise would be the difference in y values. That would be y minus f of x naught. And that's equal to the slope, which is f prime of x naught, times the run, which would be x minus x naught. Now what I'm going to do is I'm just going to solve this for y. So I'm going to add over my f of x naught. So we would get y is equal to f of x naught plus f prime of x naught times x minus x naught. Excellent. And that gives me the y value on the tangent line. Y equals f of x gives me the y value on the curve. So in order to be able to distinguish that I'm talking about the actual tangent line, what I'm going to do is I'm going to give that y value a name. Just like the y value on the curve I can call f of x, I'm going to call the y value on the line L of x. So L of x is the name I'm giving to the tangent line, and that's just f of x naught plus f prime at x naught times x minus x naught. And I want to just take a look at that formula and see what that's doing for us geometrically, and then see if we can't generalize that for functions of two variables. Notice what this is saying is that the y value of a point on the line, let's say we're talking about here, that y value there I'm going to get by taking the y value that I have here. That's my f of x naught, and I'm going to add something to it. And I can see that what I'm adding to it right there is the rise. That's the change in the y value. Okay, so this is the y value at the point of tangency. And this right here is the change in my y value on the tangent line. But I calculate that change in y by multiplying two things together. That f prime at x naught, that's a rate of change. And more specifically, it's the rate of change of y with respect to x. And then this right here is an amount of change in x. So I've got just one input variable, that's the rate of change of my output with respect to the input, times the amount that the input changes. That's going to give me the amount that the output changes. Okay, so that's my change in y. I'm just going to denote that on the picture there as dy. That's because we generally reserve delta x and delta y for when we're talking about the actual original function f, and I would use dy and dx, those differentials, when I'm talking about the tangent line. Okay, so this is just the starting y value plus the change in y, which if I wanted to, I could denote as dy. Okay, so let's see if we can't generalize that for a function of two variables. So I would be wanting to say that L of xy, again, I'm just going to give a name to this linear function that I'm creating, that I'm going to hope is a good approximation of my function of two variables, that I hope that this plane that I'm creating is going to be a good approximation of the surface that I have. Okay. And I'm going to just build it off of this model. So here, this is going to give me a formula for the z value on this plane that I'm hoping we can call the tangent plane. I do want to just point out the name tangent plane is special. So we're going to construct a function here. By the end of this video, we're not going to be confident that it has earned that special name, that we get to call it the tangent plane. In order to be called the tangent plane, it has to be a good linear approximation. Okay? And we're going to have to establish what the criteria is for being a good linear approximation, and we'll do that in the next video. Okay. But I can basically say, if this is standing for the z value on my plane, which I hope is going to earn the name of tangent plane, if I want to model it off of this, it should be similar, so it should be the z value at the point of tangency. So let's just suppose we had P naught being the point x naught, y naught, and we're trying to calculate a tangent plane there. So we would have f evaluated at P naught. So that would be the z value at the point of tangency. assuming that word applies, okay, plus some change. So I'm going to add the change in z. And I'm actually going to use differential notation for that. I can actually call that dz. Even though we don't use d's in talking about the partial derivatives that we have, I can still use the differential dz to talk about the change that I get in z. Okay. At least I'll be able to use that if this earns the name of tangent plane, which we hope it does. Okay. All right, but now, because I have a function of two variables, there are two things that can contribute to the z value changing. I could change my x value, so I could move forward or back, and that could cause the z value to change. Or I could change the y value. I could move left or right, and that could cause the z value to change. So what I'm going to do is I'm just going to calculate each of those and add them together. So what measures the rate of change of z with respect to x would be the partial derivative of f with respect to x, evaluated at the point I care about, and then I'm going to multiply that by x minus x naught. So notice that's the rate of change of z with respect to x multiplied by the amount that x changes. Exactly mirroring what we have here, multiplying a rate of change by an amount of change of the input variable to get an amount of change in the output variable. Okay. Plus, now I'm going to calculate the change that's due to y. So that would be the rate of change of z with respect to y at this particular point times the amount that y has changed, which would be the difference between y and y naught. Okay. Now I'm just going to clear some space up here so that I can label this a little bit better. So this part is the change due to x. This part is the change due to y. But both of those are calculated as a rate of change multiplied by an amount of change. I'm also going to point out that what we have right here for this dz, this change in z, that's a sum of products. We have seen a sum of products before. We get a sum of products anytime we take the dot product. So I could rewrite this as f at p naught plus this vector, f sub x at p naught, comma f sub y at p naught. That's a vector that's giving me my rates of change, plural, because there are two rates of change, dotted with x minus x naught, y minus y naught. Right? Now that really nicely mimics what we have here. Instead of just multiplication of a rate of change times an amount of change, I've got a dot product of a rates of change vector times an amounts of change vector. Very nice. So I can say the z value on this plane that we're constructing, let me go ahead and copy that down here, so L of xy, is the z value at the point of tangency, assuming that name applies, plus the change in z. And I calculate the change in z by dotting this rate of change vector with this amount of change vector. Okay. Now, this is what I'm going to call at this point my candidate for the tangent plane. If there is a tangent plane, this will be it. But in order to earn the name tangent plane, it's got to be a good linear approximation. And the fact that both partials exist so that I can create this plane isn't sufficient for that. So in the next video, we'll pick up with what is the condition that will guarantee that this is actually a good approximation of things.